The experience of having flown in space, and I'll pop up the reflections from space. I'm going to say relatively little about that personal experience. I'll start off with it in just a summary way, but if you'd like to talk about that afterward in Q&A or whatever, I'm perfectly happy to do that. So at the outset, let me simply say that the experience of having flown in space, for me, was not the immediate experience, although there's a great deal there that could be talked about and shared. But it was more the overview, the meta view, the understanding that gradually evolved after the event, integrating that into my own life and realizing that what happened to me, Nancy often says that I went up into space and came back in love with another woman, and that's entirely true, that other woman being Mother Earth, or Gaia. And I did fall in love with the Earth. Excuse me. But what does that mean? It's not the Earth as a rock, certainly. It's the Earth as the home of all life, and the understanding from that perspective, looking at the Earth from space, realizing the relationship that one has with everything that one sees on this beautiful Earth below. And this is, just one example of the incredible view that one gets when one is in space, and in particular, as in my case, having the opportunity to go outside the spacecraft, put on my snowsuit, and go out and look down at, or back, or in, as Bucky would say, to this beautiful Earth below, and realize that relationship, not just with the U.S. taxpayer who put me up there, or the U.S., but with people all around the planet, and not only people, but in fact life. One comes to understand, I came to understand at least, that this beautiful Earth, which later came to be known in some circles as Gaia, takes on a reality which is surprising, which enlarges one's understanding of oneself and life in general. This Earth is the mother of all the life that we know of for certain in the universe. Now, that I certainly believe, as I'm sure do most of you, is only a temporary situation. We will, have no doubt, find life elsewhere in the universe. But this is the home of what we know of as life. And it is a living entity. And one comes to understand that in looking at it, in thinking about it, and in seeing that relationship as you go around every hour and a half for day after day. Now, I'm not going to say much more about that, aside from pointing out that that is the foundation on which I came to form a new relationship with the institution, as it were, of life. In the 90s, NASA developed a discipline is not exactly the right word, a field of study called astrobiology. And astrobiology asked all those wonderful questions that we all were fascinated with as kids. What is it all about? What does life mean? How did it start? Where did it come from? Where else is it? Etc. And NASA took that on, gave it a label called astrobiology, and I became fascinated with looking at and understanding and puzzling where the extent and origins and nature of life in the universe. One doesn't look at life here on Earth for a millisecond in any serious way without coming to realize the power of impacts of asteroids and comets on the Earth and on the development and evolution of life. And so for the past 10 years of my life, I have spent in understanding this challenge, this opportunity, and in fact, in one dimension, this threat of the impact of these objects. Now, without the impact of asteroids and comets, we would not be here. And yet, at the same time, being here, they now pose, in addition to opportunity, a certain threat. And so what I'll be talking about tonight, first in a fairly straightforward way, I'll deal with some of the technical issues, which are kind of fun, but then I'll go into the more subjective elements of this and tie this to the challenge which we've been all wrestling with here these last few days of transparency, emergence, resurgence, convergence, et cetera, all of the things that we've been talking about. And they're all in it, and they are, in fact, the essence of it. But what I'm talking about is called planetary defense. I don't like that term. It implies Defense Department, but that's another thing. But protection of life here on Earth, the continuance of this great evolutionary experiment that we're all part of. In fact, survival. So we are all clearly familiar with natural hazards, whether starting from the top left, earthquakes or tornadoes or tsunamis, hurricanes. Natural hazards are things which can claim tremendous toll in terms of the loss of life, in agony, in creating real havoc in terms of our organized society. But when we began to look at this, and in only the most recent 2 or 3 decades, began truly understanding that there is a similar cosmic natural hazard, which is the very occasional but terribly devastating impact of asteroids and comets with the Earth. And of course, this is not just uniquely with the Earth, whether comets in the lower left and upper right or asteroids going the other direction. But the evidence of this is all around us, on the moon, on Mercury, any place where the atmosphere is relatively thin or no atmosphere at all. You see the scars of this reality that the whole inner solar system is literally orbiting the sun in a shooting gallery of these millions and millions of objects which create the scars which we see on the moon. And of course, the Earth would look like that as well were it not for the smoothing effects of weather and climate, volcanism, all sorts of things which tend to erase them. But we do have scars which are relatively recent here on Earth. Many of you may have visited the Barringer crater in the upper right in Winslow, Arizona. If you haven't, and if you're ever going to drive through Arizona, please stop and see Meteor Crater in Arizona. It's well worth the experience of being on the rim of that object. Now, these impacts have all different sizes and consequences. The one, of course, which everyone knows about or has heard about is the demise of the dinosaurs with what's referred to as the Chicxulub impact in the Yucatan, which wiped out not only the dinosaurs 65 million years ago, but 75% of all life, all species that were extant at that time, along with the dinosaurs. It was the last of the 5 mass extinctions that we know about in relatively recent, in the last billion years or so of Earth history. It was not the largest. In fact, the end Permian extinction at about 250 million years ago was larger than the Chicxulub impact. But let me point out that people think of this, 65 million years ago in dinosaurs, the immediate image that people have is way back in the beginning of, the whole solar system. This is way back. That's absolutely wrong. It's important to understand that if the solar system were 1 year old, this event occurred on December 27th. This is a very recent event. And it highlights the fact that this is not some process which happened back then and stopped. This is a continuing, ongoing process, which, from everything we can see for the last 3.9 billion years or so, has been essentially level, that is, constant. And so we are still in the same shooting gallery, and this event, which wiped out the dinosaurs, and in fact, from time to time, took a machete to the tree of life. We have this high school image of the tree of life having grown up from whatever started it, but forget that for the moment, but nevertheless, monotonically growing up, diversifying into many different branches, etc. And that's a perfectly legitimate picture, except for the fact that this crazy cosmic gardener came along with a machete and hacked off the tree of life many times in the history of the Earth. So that life did not grow up monotonically. We're not the end of some evolutionary process. We just happen to be at the very outer branches of the tree of life as it exists now. But it has had many hacks at it by this crazy cosmic gardener. And of course, like our gardens, if we take a machete to them, turn around and come back 2 weeks later, and it's rained a little bit, they're growing up again. It's a little different from the last time it grew up, but that's the cycle of growing up and being cut back and growing again and diversifying. That cycle is part of what we are a part of now. And this is just a temporary situation. Perhaps. Now the size there was, let me go back there, the size of this impact was something like 10 kilometers or 7 miles in diameter, the object here that hit the Earth. That's a very large impact. And I don't know if you can read it, but the size of the crater is about 180 kilometers in diameter. And that magnitude of impact is something that occurs only once every 100 million years. But let me point out that if you look at 45 billion, 4.5 billion years of the age of the solar system, an event of that kind has probably happened on average 45 times. So these things are episodic. This is, again, a very large one. We may or may not be due for another one. But the point is that these large impacts have tremendous power. If you try to think about how does something like this eliminate species, 75% of the species all around the planet, the magnitude of something which would do that is mind-boggling, and you have to think about it a little bit. The mechanism is not so obvious. The primary mechanism is not the incredible shock or the tsunami or whatever that occurred, but in fact, the fact that an object of this kind that hits the Earth burrows about 4 times its own diameter into the solid Earth. The atmosphere is nothing. It just disappears. A large object doesn't even pay attention, not only to the atmosphere, but even to the ocean. And it will penetrate down about 4 times its diameter. So if you've got something that's about 10 miles in diameter, or let me say 7 miles in diameter, it's coming in, it penetrates the solid Earth to about 28 miles, something like that, 25 miles below the surface of the Earth, and then explodes with 100 million megatons of energy, 100 million large nuclear weapons exploding at one time from the incredible shock and heat. And when it explodes, it takes billions of tons of Earth in a conical shape above it and throws it out into space. Some of it actually gets thrown out at such high velocity that it literally escapes the Earth and ends up circulating around and landing on Mars, maybe decades or millions of years later. But most of it ends up like an ICBM flying out and coming back into the Earth's atmosphere, half a world away or something like that, all around the world. So 45 minutes or so after an impact of this kind, billions of rocks and boulders and gas, vapor, everything comes back down into the atmosphere, and like a shooting star, in fact, a shooting star is nothing different than a small asteroid, as it comes back in and re-enters, it ignites or gets extremely hot. The whole atmosphere all around the planet gets so hot that it spontaneously ignites all vegetation around the whole planet. And so 45 minutes to an hour and a half after an impact of this kind, not only do you have rocks and dust and things flying all over the place, coming down out of the sky, but in fact you have fires all over which are putting soot and carbon up into the sky, and you end up with the equivalent of a nuclear winter. You have an impact winter. And you may not see the sunlight on the surface again for another 2 years or something of that kind. And that is what ends up killing the dinosaurs and most of life, not the shock or that kind of immediate local thing. For those who are technically minded, the thing that blew my mind when I first realized the power of this in a lecture given by a Stanford professor named Norm Sleep was that it's estimated that from this impact, because of the temperature of the sky, about 1 meter of sea level boiled off all around the world. Now that's, if you know anything about latent heat and thermodynamics, I mean, that's a mind-boggling idea. So that's at the largest scale, but they go down from there. This is Meteor Crater in Arizona. Again, you should visit this. This is a very prominent scar created about 50,000 years ago, very recent, by something on the order of 40 or 50 meters in diameter. This one in particular was not just rock, but this was iron nickel. A very small percentage, 3 to 5% of asteroids are made of iron and nickel primarily. And in fact, the pin I have in my lapel tonight is a piece of the original asteroid that created this hole in the ground. I was in the bottom of it back 40 years ago as a young astronaut learning about impact craters. This is a slightly smaller one in Australia, Wolf Crater, and of course the one which happened most recently, which was the Tunguska impact, a small object about 30 meters in diameter or so, that never even reached the ground, but in fact blew up in the atmosphere. It got hot enough coming through the atmosphere, which protects us from objects which are that size and smaller. But nevertheless, because of the downward momentum of this object, the shock wave and the heat pulse hit the ground and destroyed something on the order of 800 square miles of Siberian forest. Luckily, there were very few people. A lot of reindeer got wiped out. But had that impact occurred over a city such as London here, that's an outline of the area of devastation. And instead of millions of trees, you would have had millions of people who were wiped out. And that's the smallest of the smallest size of the objects that we are concerned about and would propose to take action with regard to. Now, unlike the Chicxulub impact, which occurs about, on average, once every 100 million years, something like the Tunguska event in the upper right occurs on the average of once every 200 to 300 years. This one was 100 years ago in Siberia, but that is the frequency of the smaller objects. So the smaller the objects, the more there are of them. This is a very normal, familiar pattern in nature. So these objects come in all different sizes. The big guy here, Lutetia, is, if I can read it, 132 by 101 by 76 kilometers, so it's pretty big. You have a couple of comets in here. Here's Halley's Comet to give you an idea. In fact, the object that we have a spacecraft just arrived about a month ago. Ceres is one of the largest asteroids, and it's considerably larger than Lutetia here. But we visited, these are actual photographs of images taken by spacecraft going by these objects. And to give you an example, here is a comet, by the way, Tempel 1, and this, I'll show you a picture of this later, that we visited this one and in fact impacted it. But here's one which we have a lot of images of. This little bitty dot here, which most of you probably can't even see, is the asteroid Itokawa, which the Japanese visited fairly recently, took a lot of pictures, and actually brought back some samples. This is Itokawa with the Roman Colosseum superposed on it to give you an idea of scale. That's about 500 meters long, and of course the Roman Colosseum is sort of dwarfed when you think about that. But notice that on this object, on this asteroid, you have very large boulders. These things take very interesting forms, and there's a great deal scientifically to learn from asteroids. These are made of primordial material out of which the solar system formed. They're, in essence, as has often been said, it's almost a cliche, an unformed planet. The remains of a planet that never quite got it all together. And most of these objects circulate around the sun between Mars and Jupiter. But we'll talk about that in a moment. And in fact, what I'll show you now is if I can pull this off correctly, let me make sure I got it here. Okay. What I'm going to show you is a movie. In the center, of course, is the sun. And the Earth, you have Mercury, Venus, and the Earth and Mars. And out here, about to disappear below the horizon, is Jupiter. And what we're looking at is from 1980 until 2011. And this is the count of asteroids that we know of. Asteroids are something which are relatively recent. We didn't know about them until a couple of hundred years ago when the first one was discovered. And in 1980, we literally knew of only a few hundred asteroids, and we started looking for them a bit more systematically. What you're looking at here is the history of that discovery. The number will be increasing. And what you see is a kind of set of white flashes. If you look at the Earth, which is this guy here, you notice outbound from the Earth, you see white pulses. Those are asteroids which are just on that date being discovered. So they flash white when they're discovered. They then convert to green for most of them, or if they come into the inner solar system, they may convert to red or yellow. Red if they come fairly close to the Earth, yellow if they're slightly less threatening. But here you see, as time goes on, more and more asteroids being discovered. Now you notice that they're pulsing, and that's because it's very interesting, but if you think about it a bit, you discover the most asteroids when when the moon is in its new moon phase. That is, when the moon is not in the sky. Telescopes don't like to have bright objects in the sky if you're trying to look for dim objects like asteroids. So it's every new moon that you end up with these flashes of white appearing. But as we go on here, you'll notice that more and more of these asteroids are in the main belt between the orbits of Mars and Jupiter, but that in fact there are a number that come into the inner solar system. And these are objects that we call near-Earth objects, or near-Earth asteroids. That is, asteroids whose orbits take them into the inner solar system. They cross the orbit of the Earth. Now here in the 1990s, late 1980s, we're seeing the tremendous number. We're up into the hundreds of thousands of asteroids, and most of them are, of course, green and in the main asteroid belt between Mars and Jupiter. But you can begin to see more and more red objects and yellow objects closer to the inner solar system. Now, in a moment here, I'm going to stop this thing so that I can make a point. Stop that. Come on, I didn't mean for you to stop. Okay. You will see here in another year or two that new spacecraft, these are all telescopic observations, generally from the ground. That's the way we discover these things every night. But from time to time, we also put up telescopes in space, and they have the most recent one, the WISE telescope, space telescope, had a slightly different pattern of discovery, which you'll see in just a moment. It was launched in 2010, and there you go, you see it now. It not only is discovering asteroids directly out from the Earth, looking opposite from the sun, out into the midnight sky, if you will, but also in what are called the sweet spots at the horizon. You look horizontally behind the Earth and in front of the Earth, and you can also discover a lot of asteroids there. The point I want to make here is that as time goes on and our telescopes are getting better, we are discovering more and more of the objects that come into the inner solar system. I'll point out that these don't orbit in circular orbits here. Most of these objects, while this is a snapshot of where they are, they actually circulate out. And so if you look around here, you'll see red objects. Some of these objects circulate out almost as far as Jupiter and come back in. But all of these red objects cross the orbit of the Earth, and therefore, because they cross the orbit of the Earth, pose a potential threat of impact. With the newer telescopes coming on in the next 10 years, the number of objects that you see out here that make this bright green band will be competed with by the bright red in here. There will be over 1 million objects. Here you see we've got 500 and some thousand objects in the main belt. We will end up discovering in the next 10 years billions of objects in the main belt, but there will be over 1 million objects which cross the orbit of the Earth. And that is the situation, the nature of the shooting gallery in which we literally live. Now I'm going to take just a moment to give you some of the, this is going to be a bit of a tutorial on orbital mechanics. Trust me, we won't get too deeply into it. It's kind of fun. But if you're looking down on the solar system with the sun up there somewhere, and this is the green line is the orbit of the Earth, and here is the orbit of a near-Earth object, or an NEO, and you see looking down on it that these two orbital paths cross. Now, of course, you realize immediately that this is only a two-dimensional presentation. So in fact, the question is this a real intersection? In other words, is this an intersection in 3 dimensions or only in 2 dimensions? There can be a great deal of space, of course, between these two orbits at that intersection. But for about 3% of the objects that we found, and we have discovered on the order of 8,000 of these objects now, for about 3% of them, this in fact is a 3-dimensional intersection. In other words, the two paths, these two lines cross where the minimum distance between them is less than the diameter of the Earth, or the radius of the Earth. And therefore, if the Earth is in this intersection, which of course it is once every year going around the sun, and the asteroid happens to be in that intersection at the same time, then we've got an impact, we've got a collision. And so the question is, when the Earth, for this particular asteroid, say, when the Earth is in that intersection, where is this asteroid? What I have here is what is typical of our knowledge of any of these asteroids. That is, it is potentially somewhere from here up to there. And we don't know exactly. This is something like this is an intersection, let's say, or this is a potential impact, a potential collision, 20 years in the future. We have looked at this asteroid, we've plotted its path, and we forecast where it's going to be for 100 years into the future. And this may represent a date 20 years from now where, in fact, there is some probability, if you think of this white line as 1 million virtual asteroids, one of which is the actual asteroid, then if any of these million objects, there is a certain percentage of them, say 1/50th of them or something like that, which lie between here and here. In other words, they will be in the intersection at the same time as the Earth, and therefore there'll be an impact. So with this particular asteroid and this geometry, this level of uncertainty of where it will be 20 years from now, we would say the probability of impact is something like 1 in 50. Now, that's done mathematically and quite accurately, but I'm approximating here to give you the idea. Now, obviously, if the real asteroid is one of these dots up here, then it will have gone through the intersection before the Earth got there. Conversely, if it's one of these, it will arrive after the Earth has already gotten through the intersection, and it will not impact the Earth. But if it's one in that small segment, then there will be an impact. And that's what we're looking at. Now, the other thing I want to point out here, just for those of you who are somewhat mechanically oriented, let me say, or technically oriented, what's important here is the relative velocity. The asteroid has a velocity represented by this vector, the Earth by this vector. The relative velocity is that third part of the triangle. In other words, if you were on the asteroid, that's where you would apparently come from. You would appear to come from that direction and hitting the Earth. Think of the Earth and the asteroid both coming along these lines at approximately the same velocity. So if you're here and the Earth is here, you're going to have to look toward the sun to see the Earth. Similarly, as you come along this orbital path, you will continue to look in that direction. So the relative velocity is, excuse me, let me go back again. One more time. The relative velocity is like that. What I want to do here is ask you to picture yourself sitting on that asteroid headed for an impact with the Earth. Now, if you're headed for the Earth, you're in a plane here, and that plane intersects the Earth along that red line. Looked at in this Google Earth perspective, here's the Earth, and it's oriented correctly for this particular asteroid, which I've drawn here, which is the asteroid Apophis, which some of you have heard about. And there is a very small probability that this asteroid will hit the Earth in 2036 on, believe it or not, Friday the 13th of April, 2036. Now, the probability is very low. It's not something to worry about, but it's one we've studied a lot. And this is the orientation of the Earth, that if you're riding that asteroid headed toward an impact, this is what you'll see. But because we don't know exactly where that asteroid is going to be, you may be one of these dots over here, and you may pass behind the Earth, or you may be on a dot out here and pass in front of the Earth. But if you are in that segment of the orbit, you will be hitting the Earth along that line somewhere. You will not hit down here or up here. You're going to hit somewhere along that very narrow line. We know that quite precisely. The big uncertainty about our knowledge of where this asteroid is in fact going to be in 2036 is along this line. It's not the orientation of the line. The line is very, very well known. Okay, now I want you to keep that picture in mind. That's the kind of work that we do today in the what can be called the early warning program. Okay, we use telescopes to find these things. We plot their orbit. We predict where they're going to be for the next Hello? Did I do that? I don't think so. We predict where they're going to be for the next 100 years and find out whether there's going to be any possibility of an impact. And of the 8,300 or so objects that we found as of this morning, 368 of them, about 3%, have a non-zero probability of impact. In other words, some small or slightly larger probability of impact in the next 100 years. Okay, if we find one with our address on it, what do we do about it? We want to deflect it. And I'm not going to go into any detail here, but let me just say that there are a couple of techniques that we can use for deflection of an asteroid, which is a very simple matter. All you want to do to deflect an asteroid, to cause it not to impact when it otherwise would, is to make it arrive a little bit earlier than it would by changing its orbit very slightly, or to make it arrive slightly later than it would. If we can change its arrival time 20 years down the road by 8 minutes, it will arrive and go through the intersection before the Earth gets there instead of at the same time. Or if we make it arrive late by 8 minutes or more, the Earth will be through the intersection before the asteroid gets there. And that is a successful deflection. How do we do that? We run into it. Literally, you rear end it. You go up there, you run into it. That's what we did with Comet Tempel 1. This is that same comet that I showed in an earlier thing, and this was the impact when we ran into Comet Tempel 1. We didn't do that back here we go again, July 4th, 2005. We didn't do that in order to create fireworks. In a way, we did. We created fireworks not to change its orbit, but in fact, in this case, to splash out some of its guts so that we could measure what it was made of. Okay. But nevertheless, we know how to run into things. And if you run into things the same way as your Mini Cooper running into an 18-wheeler, you're going to change its velocity slightly. A gravity tractor, I won't even go into it, but here we don't even touch the asteroid at all. We simply hover in front of the asteroid while it's tumbling there, and we can pull it toward us just with our mutual gravity. Now, I'm simply going to say that we can do both of these two technical issues. We can find asteroids and predict where they're going to be in the future and have an idea of whether or not, at least we can determine probabilities of whether or not there's going to be an impact, and we can deflect them if, in fact, we find that one has our address on it. However, the third issue, the third requirement in terms of protecting life on Earth is a bit trickier. Now, this is simply the same view you saw of the Google Earth sphere, except here we have it laid out on a Mercator projection of the Earth. And this is that same line that you saw, that red line coming down across the Pacific and across the Isthmus of Panama, et cetera, and starting over here in Russia. Now, what I want to point out is that since let's just imagine that the actual impact point is in the middle of the Pacific. Now, if we cause this asteroid in our deflection process to arrive early, it's going to hit here instead of there, or here, or here. In fact, what we're really doing in a deflection is we're dragging the impact point along this line by making it arrive earlier and earlier until it goes off the edge of the Earth. That is, the impact point misses the Earth entirely. We end up going through the intersection before the Earth gets there. Or, conversely, we cause the asteroid to arrive late, in which case the deflection will cause the impact point to shift along the line until we get it off over here, in which case we declare great success and open the champagne. Now, the reality comes, somebody's got to make a decision here. Number one, do we deflect it? Who pays for it, et cetera, who deflects it? But also, which way do we deflect it? The people here in Nicaragua say, hey, deflect it that way. And the Russians and the Japanese and a few other people over here say, hey, drag it off the leading edge of the Earth. Okay? Now, turn the Earth a little bit and change the line, make it one that's going to hit in the North Atlantic and go over the United States on the western end, say, and Europe and Russia. So what do? Do we race the Russians up there to see who pushes it over who? This has to be a collective decision. The decision-making of do we deflect, how do we deflect, who pays for it, who handles liability, all of that has to be a transparent process in which all nations are involved in a collective decision to protect life on Earth from this impact. Mechanically, it's pretty easy to do. It's not even expensive, relatively speaking. The United States could do it, India could do it, Japan could do it, China can do it, Russia can do it, Europe can do it. We're all spacefaring nations. But who is going to do it? And what technologies are acceptable? Can we use nuclear weapons, etc.? Why are we getting that? Oh, okay. So this has to be a collective decision of the world community. And it is that element of it, not the technical elements of early warning or deflection, but rather the geopolitical decision of making a commitment to do this or let it hit or argue until it hits, okay? Which is the most likely thing to happen, in fact. But that geopolitical effort is what brings us to the meeting that we've been having here. We have an emerging problem, okay? We've got to have convergence, we've got to have transcendence in order to, in fact, protect the Earth from these potential impacts. Now, this is simply one actual case. Below here, what I've shown is a hypothetical situation about 10 years from now where we're going to have hundreds of objects with a higher probability than Apophis of impacting the Earth. And there's not a nation in the world which is not going to have one or more lines going across it. So this is not some academic issue in which Colombia, Venezuela, Nicaragua, and Costa Rica and Russia have to concern themselves, but it's an issue for the whole world. And it is that decision-making, that geopolitical decision-making process, which comprises the third essential element in protecting the Earth and life on Earth from extinction, potentially. I mean, 99.9% of the time, it's going to be a sub-extinction event, but nevertheless, that is the ultimate worst case. And so this is, again, another organization which I started, but which I led the effort here to bring astronauts and cosmonauts from around the world, along with experts, diplomats, legal experts, political people around the world to address this extremely difficult decision-making process where, in the end, there will be elected and some non-elected national leaders who will end up having to make a decision whether or not to accept a temporary increase in risk should a deflection go bad in order to eliminate the risk to all life on Earth. And that is an extremely difficult and challenging geopolitical decision to make. We therefore, in 2005, began this geopolitical element of the asteroid threat response issue. This is simply a 2009 photograph with me in the back of the Outer Space Committee of the United Nations presenting the results of our recommendation on a decision process to the United Nations. And this is a process which is now ongoing. Now, coming back to where we are. You can imagine, if you put yourself in the position of a world leader, and these are the representatives of the leaders of the world, dealing with, being confronted with an issue which is simply a matter of time. It's not a question of whether this will happen, There is absolutely no question we will be confronted collectively with this challenge. And this can be from a regional disaster to a local disaster, up to regional or up to continent-wide, or for that matter, a planetary challenge. And any of those, in fact, all of those, will appear in the future. This is a process which has gone on for the last 4.5 billion years. It brought to the earth water, which has enabled life, as well as hydrocarbons. And at the same time, it has destroyed life ever since, in the form of dinosaurs and many, many thousands of species which have been eliminated by impacts in the past. And of course, the question that confronts this new group of dominant animals, representing all life on Earth and not just human life, are we going to do something about this, knowing ahead of time that we are able to predict it and that we have the technology to prevent this? The question is, do we understand our common humanity, our shared humanity? Do we have enough convergence to understand that we are one life in this small corner of the universe? We are an evolutionary experiment here on the local, in this local corner. We don't know where it's going in the future, but we are being born into the cosmos. We are living at the moment of cosmic birth, where out of Gaia, life is emerging into the universe locally. These are the representatives who will end up deciding whether or not we rise collectively to meet this challenge. Do we, in fact, understand, as Archibald MacLeish did in this beautiful poem that he wrote back in 1968, when the first people went around the moon? Do we truly forget the chauvinism in it, but do we really understand that we are brothers who know that they are truly brothers in this eternal cold? When we look out into the universe in the Hubble Deep Field, as was shown, actually, it's a nice little sandwich in the first presentation, in our time together. Every dot of light that one sees here is not a star, but a galaxy. Every dot of light represents not only hundreds of billions of stars, but also 10 times, something like that, 8 to 10 times that many planets. And undoubtedly, in my mind, there is out there life. This process, which has created a sun with planets circling it and asteroids and comets, is not unusual. We have already seen evidence of asteroids and comets around other stars, nearby stars, that we've been able to deduce that there are, in fact, asteroids and comets. This is a common process. And therefore, for me, looking out there, it is clear that if there is, in fact, a community of sentient life out there in that large universe, its members have each faced this challenge and passed it. One doesn't become part of a community of life beyond one's own star system without having protected life on your home planet from this near-term challenge, this challenge of impacts. We humans now face this great test of admission. And the question is, do we understand? Can we be transparent enough with one another? Can we be honest enough? Do we have enough convergence to understand that we are children of Gaia moving out into the universe, and that this is a tremendous responsibility? And we all share it, and I thank you for allowing me to talk to you.